Okay, so we're moving up to the next speaker, who is Professor Hanoch Levy from computer science, and he will tell us about super spreaders.
תודה על האינטרודקשן, תודה על הארגון של הכנס. תן לנו אולי הזדמנות למצוא שיתופי פעולה מעניינים. תודה על האתגר שנתת לי שאסור לי לזוז עכשיו, אני צריך להתרגל לתת הרצאה בלי לזוז. הנושא שלנו, נושא שעבודה משותפת שלי ושל סטודנט שלי יונתן תבורי שיושב כאן, מטפל בתופעה של הסופר ספרדינג שמצאו אותה בקוביד בצורה די משמעותית, ואיך הסופר ספרדינג הזה משפיע על ההתפתחות של המגפה. Anybody wants one in English? I think so, yeah. Okay. So let me say again, the most important part was thank you for everybody. Thank you for the conference. We're looking for possibly collaborations. And Jhonatan Tavori is my student, he's my collaborator here. And our subject is to deal with super spreading, which appeared or discovered in COVID in a very significant way. And more importantly, how this super spreading affects on the development of the pandemic and how we can use the knowledge of this super spreading to affect policies on lockdowns and on vaccination strategies. That's the subject of the topic. The outset of this story is back in early 2020, what I call World War 2020. These are the bad guys, and the whole world is trying to fight the bad guys with all these kind of stupid measures of masks, alcohol, and lockdowns. And in the middle of all this, there's a new celeb. The new celeb is perhaps the most celebrated scientific measure ever, which is, I would call it Mr. R. So Mr. R appears in the news every day, and Mr. R, every day we watch what R is. And who is Mr. R? R measures how the disease is transferred, how transferable the disease is. And very simply saying is the average expected number of persons that an infected person would infect. For example, if R is 3, then it's very scary. It means that every infected person infects 3 persons. And this is real, then COVID would go to the sky in very few months. This was the original estimation for COVID, 3, very scary. On the other side, there's R less than 1. This is a wish and dream of everybody on COVID, that R will go below 1, and we looked at the paper every day and watched and hoped that R will go below 1, because when R goes below 1, the pandemic dies out, the spread dies out. And this is called herd immunity. So herd immunity is what we are after, or R less than 1 is what we are after. So a few words about what is herd immunity or herd immunity threshold. Traditionally, we have been using a model which we're still using, the simple model of SEER model, says that every individual starts as susceptible. Sometimes along the pandemic, the individual becomes infected for some time, maybe a week or so. And then after that, the individual either recovers or, God forbid, is removed. Both are with R, so it helps the model. The traditional assumption prior to COVID was the population is homogeneous. Homogeneous means in how individuals are infecting others. It's all homogeneous, And under homogeneous population, everybody infects the same. Under these assumptions, the development of R along the pandemics is very simple. It's linear. It operates as a linear function. If this is the fraction of people that got infected, and this is R, it starts with some number. In COVID, it started at 3, and then it goes slowly, linearly along time, where the most critical point at this point, which is when R reaches 1, that's a herd immunity. That's what everybody prays for, and that's where the pandemic starts dying out. For COVID, when the numbers at starting were 3, under the linear model, it says that 70% of the population, more or less, have to be infected before herd immunity is achieved. Very scary number. 70% of the world would have to be infected before the pandemic would die out. What happened in the early summer 2020? On the political side, there were very good news. I think many people here, or many people in the world, or many people in Israel, believe that the war is over. Some people may even started drinking beer. And in the scientific front, people have discovered super spreading. And super spreading is basically a heterogeneity of the spreading. What super spreading says is that spreading is not homogeneous. Some people infect more, some people infect less. And for example, if this is the distribution of infection, then this axis says how many people would you infect, and this says which fraction of population infects. If you look at this plot of under gamma distribution, it says that very small fraction of the population will be as super spreaders. They will infect a lot. And most of the population will infect very little. That's super spreading. And for COVID, people estimated this curve, a gamma with parameter 0.1, starting at R equal 3. Following these observations that was made in the community, came up several models that tried to ask what will happen to the pandemic under super spreading. If we assume that super spreading is what we have, what will happen to the herd immunity threshold? And results started being much more optimistic. The 70% dropped down by one study to 43%, by another study to 5%. In particular, this study that got us into research was born in this university, Oz, Rubinstein, and Safra, came up with a mathematical model that accounts for heterogeneity, and the mathematical model reaches the conclusion that COVID will die out at 5%. This 5% and this good news of the end of the first wave brought us all into kind of euphoria. That's early summer 2020. And before going to progress on time, let me explain to you why we dropped 70% to 5%. It's all due to super spreading. We're talking about super spreading that few persons or small fraction of the population infects a lot, large fraction of the population infects a little. And the model says the following. Each individual has some infection level and some susceptibility level. The assumption of the model says that they're equal. I know that some biologists here will object it. We'll talk about this in a moment. But the assumption of the model is based on the fact that susceptibility and infectionness are social features. They reflect how many contacts you have in the population. If you have a lot of contacts, you are more infectious. If you have a lot of contacts, you are more susceptible, and therefore the two things go together. And if you have less contacts, you are less. Basically, if you're talking about super spreading versus not super spreading, You can take example, for example, on this side of the curves with the super spreaders. For example, a cashier in a supermarket will have a lot of contacts. The cashier will be a super spreader. On the other hand, a researcher that works in the lab, maybe not biology labs, but more computer science labs, basically works with a computer. The only virus that a scientist can meet is a computer virus. So he is a very light spreader. So this is a model. And under this model, what happens to the evolution of the pandemic? Under this model, we're asking along the propagation of the pandemic, who is going to be infected on the ith stage of the pandemics. And who is going to be infected is given by the personal trait of the person. It's the susceptibility of the person divided by the susceptibility of all other persons. And you can see from here that a very susceptible person is likely to be infected first. Therefore, super spreaders under this model are infected first in the game. And if they are infected first in the game, they leave the game. And when they leave the game, the pandemic dies out fast. So if the traditional model says that the pandemic dies out slowly and dies out at 70%, the heterogeneous model or the super spreading model says pandemic dies out much faster and reaches the herd immunity at around 5%. That's the explanation. And that's the basics of the whole analysis. So good news and very optimistic in early summer of 2020. And what happened in late summer 2020? Some of you call it wave 2. But what we saw is two things. First of all, we noticed that around 5% of the population was already infected, but the pandemic didn't die out. On the other hand, we see the news that look like this. There are a lot of infections happening in weddings and events. I call it the wedding wave. And we ask what's happening. How come that the theory says the super spreaders are out of the game, but we'll still see a lot of super spreading? So super spreaders are out, but there's a lot of super spreading. And we try to put these two things into a model. And the rationale for the model that we came up with was these two observations. Super spreaders are out, but they're still super spreading. So if we want to take the model and deal with those two features, we say, okay, this is very valid. There are super spreaders, there are light spreaders, but in addition to super spreaders and light spreaders, there are eventual events that are not accounted for. In these events, everybody goes to weddings, not only people who work in the supermarket. So in events, everybody is becoming super spreader. So we wanted to create a model that accounts for both factors. And we took the model of Oz, Rubinstein, Safra, and extended it to deal with two stochastic processes that run in parallel. One stochastic process takes care of this part, identical in a sense to their model. The other stochastic process takes care of this, and they are combined together, and we analyze that model. Summary of the results of what we have here. First of all, we extended the reproduction model. Second, we analyze the model and derive the herd immunity under the model. And more interesting from my point of view, is we analyzed lockdowns under this model. And what we showed is that not all lockdowns are born equal. Different lockdowns are different. Some lockdowns may act positively in the long run and reduce the herd immunity threshold, as we want. But other lockdowns may be counterproductive and actually increase the herd immunity threshold, namely be counterproductive on the development of the pandemics. Let me go a little bit to the details. So we have this model with two spreading functions. And spreading function consists of two functions. One is a personal trait function. That's what every individual carries with him. Under this personal trait, the cashier has a large spreading factor, and the scientist in the lab has low personal trait factor. And these are drawn one time because this goes with you all along the pandemics. On the other hand, there's event-based infectiousness and susceptibility. And these are stochastic variables that are redrawn every day. Every day you are randomly, either you go to a wedding or you don't go to a wedding. And the overall infectiousness or susceptibility of a person consists of the mix of these two things. There's a mix of how much you are using your personal traits and how much you're going to weddings. And the mix is this P. And in fact, P could be a social factor, because some societies have a lot of weddings or a lot of events, and then they will have a large, a small P. And some societies have less events, and the P will be larger. So it's a social thing, the mixture between personal and event spreading. And the two factors, the two spreading factors, are drastically different on how they progress. Because one of them progresses in one way, the other one progresses in a different way, and we have to track their combined progression. When we do this, as I said, P is a mixture between the two and depends on the society. And the important assumption that we have is the expected conditional infectiousness. This is the expected conditional infectiousness. It depends how much you are infective depending on how much you are susceptible. That's conditional dependency between infectiousness and susceptibility. And we only assume that this is monotonic in susceptibility. Or it's not, it's only monotonic. That's the only assumption we have. And once we have this assumption, we analyze the density of the susceptibility in the population. We track along the process of the pandemic what fraction of the population is very infective, what fraction is less infective. Or in a sense, if you want to see it here, we start the pandemic with a lot of people which are very little infective, some medium, and some very heavy infector, very heavy spreaders. And along the evolution, heavy spreaders die out, and we left with less heavy spreaders. That's this distribution that we track. And once we compute this factor, we can compute the celebrated R as function of N, where N is the development of the pandemics. There is a question that if I talk to biologists, the question will come up: what is personal spreading, namely infectiousness and susceptibility? Is it due to contacts, which is the model of Oz, Rubinstein, Safra, or biologists might say, some of them might say that this is some biological features of a person. What we require is basically that susceptibility, expected susceptibility, expected infectiousness will be monotonic in the susceptibility. Now, if you want to think about a combined model of biological and social spreading, you may say, okay, I have infectiousness due to biological terms, and I have infectiousness due to contact, 5 minutes, okay. And if this is what you have, then we may assume that these are equal. The number of contacts is equal for infections and susceptibility, and we only require monotonicity on the biological term, which I think is quite reasonable under wide assumptions. I'll be glad to ask biologists whether they think this is right. Let me go to results. So here's how R progresses on the pandemic. And the nice thing is that you can split R to contributing factors due to events or due to personnel. And you see that events are dying out slowly, personnel dies out quickly. What does it do on the herd immunity? We can see that societies, here we plot the herd immunity as a function of heterogeneity and the relative weight between events and personnel. Here the bottom is a very good situation. It's very heterogeneous population and there are not many events, only 5%, but if you increase homogeneity or you increase events, things get very bad. How it affects lockdowns, and I want to sum up with this. Lockdowns was a main measure we took to fight the pandemics in the early stages. And we can think about various lockdown strategies. I can think along our model with two major lockdown strategies. One that lockdowns the personal traits. Let's say lockdown on workplaces would lock down the personal traits. Lockdown on events, on weddings, will lock down the events. And the question is, what kind of lockdown is more effective? And the thing is that the type of lockdown you take affects not only how many infected, but they also affect who is infected. Let me see this. I think this curve shows it, but we don't have the time. So let me see what the results say. We have two theorems here. One says that if we take personal trait spreading targeted lockdowns, namely lockdowns on workplaces, we will increase the HAT. Namely, if you put a lockdown on workplaces, you increase the HAT. It's not so good. Nonetheless, if you put lockdowns on weddings, you will decrease the HAT. So the two things work in opposite directions. I will not talk about the proof, and I just want to demonstrate how it works. So here is we did in some simulation or some analysis. Here you can see an event on social, a lockdown on social events, okay? And the blue curve says what happens without lockdown. Red curve shows what happens on with a lockdown. So with the lockdowns, during the lockdown, the big drop on R. But as you come back from the lockdown, things are still good. So if you put a lockdown on events, you win in the short term, and you also win in the long term. On the other hand, if you go to lockdown on personal traits, during the lockdown, you win. But as you lift the lockdown, R jumps very high, and you end up with worse pandemics on the long run. If you want to see the number of infected, we took here simulation. The blue line says number of infected along the pandemics without lockdown. Here we took two types of lockdowns, one on personal trait, one on event-based. We made them to be equal along the lockdown. But then what happens after the lockdown? The personal trait lockdown brings a lot of infected person. The event-based being much less. And if you count the total number of infected persons, no lockdowns is a blue. The red one is here, and the green one is here. One does good, one does worse. December 2020 brought vaccinations, but we are out of time. So I'll keep the vaccination story, our analysis of the vaccination story, to maybe to the next conference that we will have. And let me summarize that. Thank you.
Thank you so much for a fascinating talk. We have time for 2 questions. Yeah.
Why is the jump, the big jump after the lockdown? What's the motivation?
You're talking here?
Yeah, here.
You're talking about this?
On the right, why do you have the big jump after the lockdown?
First of all, both of them show big jump. And the big jump is very clear because you put everybody at home, so the R is artificially compressed. But when you release people, they're still there. The super spreaders are out. Those you put the cashier back in the cashier place. The cashier gets the virus from someone, and the whole thing blows up. That's what happens here. That's exactly these are the cashiers. These are the cashiers that under normal evolution, the cashiers would go out of the game here, but you left them at home, so they're coming back.
Okay, thank you.